We are going to continue with substitution problems today, and this will be the last time you ever actually are learning substitution. In every class after this, whether it be my class this semester, 151 next semester, 252 the semester after, differential equations after that, you're going to be using versions of substitution, but you're already going to know how to do them. So this is really the last time you're going to get instruction on how to do it. What's funny is the last day in my Calc 3 class, I had to spend some time going over exactly what we did. How to do definite integrals that involve substitution. Because a lot of the folks in that class, they're not really clear, so they're writing things that are not necessarily true, but I'm getting the right answer in the end. I'd actually show them, no, you actually have 3 completely different numerical answers and you're putting equal signs between them. Okay, that's sort of the equivalent of taking the multiple choice test and filling in all the bubbles and saying, but I got the right answer. No, you got 4 wrong answers, circling both true and false. So what we want to do is we want to be right, but we want to know that we're right, and we want to easily be able to represent it, explain it to someone else, that sort of thing. So let's start with a couple of problems. They're relatively simple. Okay? Excuse me. Okay, tell me something about these 2 problems. There's an infinite number of versions I could ask, or I can keep messing with that thing right there. But tell me something about these 2 problems. First of all, the obvious, are they exactly the same? No. No, but what is exactly the same?
Numerator.
Well, bigger picture. Are you going to have to do a substitution on these?
Yes.
Yes.
So tell me about the substitution of these 2 problems. It's going to be
The same.
the same. That's the key. You're going to do the exact same substitution, but they're 2 completely different problems. But this is not unusual, and this is where the deeper understanding is going to take place. Yes, it's one thing to navigate through a problem when you're practicing in a homework of a section and all the problems are basically the same thing over and over again. It's really easy to do it, isn't it? Then you go to the next section, different problems, you do all those. But then you get to the chapter review where all the problems are randomized, and now it's tougher because you have to say, what category does this fall into? Well, this is exactly what integration is going to become for everybody in this room for every semester from this point on in mathematics. You have to do integrations. Yes, you're going to do a substitution, but what is the form of the integration? You have right now 20 integral forms. They're on that sheet that I gave you before the semester. Things like u to the n, sine u. Right? 1 over u du. These are integral forms. These don't look like any of those, but through the appropriate substitution, I make these look like one of those. But the bigger picture is not what's the final answer. It's what form does it take on, because that determines my substitution and the route I take. So in both of these, let's start with the substitution. So what part of this problem do you want to call the u?
3x squared plus 6x plus 3.
Do I want to include an exponent in that? No. I don't want to include it because then that'll just make this a u cubed on the bottom. That'll make that just a u on the bottom. My du?
6x plus 6.
6x plus 6 dx. Now, so well, you know, I keep forgetting to put that on there. Actually, the most important part, that's actually the most important part of the problem. You're changing the instruction from an instruction to integrate with respect to x to an instruction to integrate with respect to u. You need both of those symbols there. And a lot of times we get really careless here. This is easy, but if I'm careless, that goes with that. These can't be different, so I have to make my substitutions appropriately. Do I have a 6x plus 6 in either numerator?
No.
Not yet, but I do have a multiple. What do you think would be a good idea right now to do, maybe to that thing?
Take the 6 out of it.
Factor out the 6 for the simple reason it might make it easier to identify. I don't have a 6x plus 6, but do I have an x plus 1?
Yes.
Yes, and I'm only differing by a constant multiple. Constant multiples we can live with. I can't do it if the exponents don't match. If that were an x squared, for example, I cannot do this substitution. It doesn't mean I can't do the problem. It means I can't do this substitution, which probably means it's not a Calc 1 problem. That automatically means it's a Calc 2 problem. And we're not going to do any of those. So I can do this beautifully. So what do I need? In both cases, what do I need? I need a 6. Because I need 6x plus 6 in both of these. I just made both integrals 6 times bigger.
That's y by 6 on the outside.
So how about a 1/6 on the outside? I'm good there? Great. I want to do my substitutions. 0 to 1 is the range of values for x.
Just to change the limits for.
Yeah, so I'm going to show you something here for a moment. Let's do both of these. Can I say this? Can I write it? I'm going to rewrite this one, but not the other one. Or actually, I'm sorry. I'm going to rewrite that one. I'm looking at the wrong one. Sorry. The negative, it's the exponent here. I'm going to rewrite this one. That other one's fine. So I'm going to rewrite this one to the negative third power, 6x plus 6 dx. You do not have to do this, but this is often a wise move because now when I do my substitution, what's my new integrand going to look like?
U to the negative third.
U to the negative 3 du. It's much easier to look at u to the negative 3 than it is 1 over u cubed. Right? I can't have the exponent be in the denominator and integrate that. I need the exponent here. I don't need anybody to rewrite this, but most people would find it wise perhaps, because this is the thing I'm going to integrate. I don't want to write 1 over u cubed because that doesn't look like anything. Just like I don't want a square root of something, I want something to the 1/2 power. It's easier to interpret. This one, because the denominator is just the same thing, I don't need to do anything here. Can I just do this 1 over u du? Can I just do that? Yeah, that one's easier. Could I have gone directly to this? Could I have gone from here to here?
Yes.
Absolutely. And my hope is that everybody here will do that. I don't need you to do that today, but I do need you to do that at some point because we're going sideways here. This is correct and it makes it easier to interpret. But as long as you're looking at this and you're seeing it's an exponent of negative 3, you can go right to there. Piece of cake. Now, what do you think about this? Well, let's continue this one just for now. This is going to be what? 1/6 natural log absolute value of u from 0 to 1. Hey, so far so good, right? In the left eye wing.
Are you going to change the limits?
Well, right about now, you hear the red light in the background. Right, we're DEFCON 3, DEFCON 4, I don't know, it's bad. Right, the nukes are headed this way. I've just caused a world calamity here because I wrote something mathematically impossible. I taught Chuck Norris how to divide by 0 and to count to infinity. I take great pride in that. Counting to infinity is easy, just count by 5s. But even Chuck can't take the natural log of 0. That cannot be done mathematically. I have an egregious error here because of why, Chase?
The limits, you're going to change them.
I got the wrong limits of integration. You can't ever change the variable back in a definite integral, and you can't change the limits once you state the limits. So the moment I got to here, it's a disaster. So I got to fix it here. I can't fix it here because now I'm putting an equal sign between completely different numerical values. So it was always here. Now, whatever limits I get here, am I going to get? I think, actually, you know what? I think the problem is, well, it has juice, but I think the juice might be getting low. So this 0 to 1 is incorrect in both cases, but the nice thing about this problem, the substitution was exactly the same. Your new limits of integration are going to be exactly the same. Your antiderivatives will not, but the setup up to that point. So how do I figure out my new limits? Well, this is the key right there. That's my substitution. So as x is ranging from 0 to 1, And you can think of u as being u of x. So when x is 0, what is the value of u?
3.
3. When x is 1, what is the value of u?
12.
12. And so all I need to do is 3 to 12 for both of these. Now, both of these integrals are really simple. There is absolutely nothing challenging about either one of these at this point. The original questions, they look terrifying because I cannot integrate either one of these as is. You have 20 basic forms and none of them look like this. They look like u to the n. They look like 1 over u. They look like sine and cosine of u. They don't look like bunch of stuff over bunch of stuff. But once I make the substitution, I get something that looks like this. This is now a piece of cake. So this is what? 1/6, just like before, log absolute value of u, but now I'm ranging from 3 to 12. I don't need to write absolute value of 12, it's already 12. I don't need to write absolute value of 3. Now, this is a good final answer. Do you have a better final answer? What do you want to do?
ln4,
And how did you do that?
12 divided by 3.
Because the difference of the logs is the log of the quotient, and here's that case where they're multiples of each other. This is the time I would do that. It's 12 over 3 or log 4. If it were not 12 and 3, but maybe 12 and 5, I would probably leave it. It's still correct to do that, but I think log of a fraction starts getting uglier, and if you're doing this on a calculator, there's more opportunity for errors because it's an odd entry. But this is nice. So that is the final answer. Leave the 1/6 in front. Putting it up as an exponent is actually going backwards. That's not making it simpler. Now, what's the antiderivative of this? U to what power?
-2.
-2 over negative.
So times 1 over -2, so negative 1 over 12.
Oh, yeah.
So far, so good?
Yeah.
Bless you. Do you want to write 12 to the -2? Or can I write 1 over 12 squared? Might that be easier? I'm going to do this in my calculator. And then what would the other one be? 1 over 3 squared. Now do that on your calculator. The answer is rational. Now let's see what we get. Anybody got an answer?
5 over 576.
5 over 576. Okay? Worked out pretty nicely. The final answers don't have anything to do with each other. They look completely different. The antiderivatives look different, but the way I set up the problem, the substitutions were the same. Now, I am notorious for doing crazy, evil things of this nature. Well, not exactly. But I love asking questions where the integrands look similar because it means that you have to look at it and you have to categorize it. It's really easy when you're doing the same type of problem over and over and over again to get good at that type of problem. But when you have 20 integral forms and you might have 20 different integrals sitting in front of you, like a chapter review would have, saying, oh, this is one of these, this is one of these. The moment you can categorize the integral, meaning when you looked at this, the moment you see that this is going to be of the form 1 over u du, and this was going to be of the form u to the n du, the moment you could see that, it means you're going to easily be able to finish the problem. But if you can't see that, you won't know where to go next. Okay, then it's kind of a dead end thing. Okay, let's do a little bit more now. I want to do a little bit with inverse trig. So we saw before, we did this I don't know, a week ago or so, that if we had something of the form 1 over a squared plus u squared, I'm going to be the most generic humanly possible. The u means we probably already did the substitution. Then what is this answer? Well, which of the functions, first of all, does this look like?
Tan inverse.
So inverse tan, as opposed to the other guys. Assume a is not 1. It could be 1, but it's probably not. Where does the a show up? How many times does the a show up?
2
2. Where?
in front,
In front?
reverse, and
And
DU.
here. Now, I'm going to leave it right there because I don't know what my original substitution was, but there's the antiderivative. Okay? The most common mistake is probably to forget that guy there. What I noticed that a lot of folks did on their quiz was they went through and they re-derived this antiderivative from scratch. Why? Yeah. Well, I factored out the a squared, then I made it u over a quantity squared. And by the way, almost everybody did that got the wrong answer because they forgot there was a chain rule factor that they now messed up. No, that's a straight up formula. I don't have to do much. Okay? So what if I have something of this form and now I have a definite integral? So let's do an example. I'll start with a simple one. I always like simple. Let's see. It's really not that important what the final numerical value is. It's doing the correct substitution and thereby getting the correct antiderivative. Were any of you worried what this was going to look like on the last step? No, you were interested in getting this. The rest just sort of flows. So that's our goal. I cannot integrate that. There's no formula that looks anything like that. In fact, the inverse tan formula has a 1 in the numerator, doesn't it? So, I'm going to really make this terrible, by the way. I'm going to give you the companion problem. I like to call it the sister problem. This is a bigger picture. This is how it's always going to be. Would you say these two look really similar?
Mm-hmm.
In fact, they look more similar than the first two. Are they the same?
No.
Not at all. Oh my gosh. There is a priority, and I want you to realize that if you use this priority, it will make your life easier most of the time. When I see a quotient, and by the way, this was a quotient, but this had no exponents in the denominator. The fact that I had exponents in the denominator meant almost certainly this had to be of the form u to a power. This did not have an exponent in the bottom. So we kind of lucked out because the degree of the numerator was what?
1 less.
1 less. When the degree of the numerator is 1 less, I'll give you a hint. In Calc 1, when the degree of the numerator is 1 less, it's always going to be the derivative. In Calc 2, it's never going to be the derivative. You've got to do other stuff. But in Calc 1, it always works out just so beautifully. In those two problems, which one is the easier one to examine, do you think? The first or the second?
The second.
The second, because the degree is 1 less. So thereby, the numerator, there's a really good chance the numerator is the derivative of the denominator, or at least a scalar multiple. And if that's the case, that's the easier of the two. So let's do that one first. So am I going to do the same substitution in these two problems?
No.
No, for that reason. So here, what am I going to call my u?
16 plus x to the
So the
4th.
whole denominator, correct? And if I do that, then what's my du?
4x cubed.
4x cubed dx do I have? Heck, I have twice that much. Is that a good thing? Oh, that's an excellent thing.
Mm-hmm.
If that's not a 3, if that's a 4, a 5, a 2, heck, a 5 halves, that's bad. But it's perfect. I need a 4 here, I have an 8. What can I do? Can I do that? 2 on the outside? So that's 2 times 4. How about my limits of integration? X is going to range from 0 to 2, so u will range from
16 to 32.
0 is the easier of the two. 16 to 32. So this is now 2 times the integral from 16 to 32 of 1 over u du. Because all of that is my du right there. Do we like this one? Oh, yes. U to the n is probably the most common, but a close second would be 1 over u. And they look at the first two problems. They look very similar, don't they? One has an exponent on the bottom, the other one didn't. So at this point, what do I have here? 2 log from 16 to 32, which is 2 log 32 minus log 16. Is that a situation where I should combine them again? Yes. So my final bestest answer is 2 log 2. By the way, is 2 log 2 equal to log 4? I'm seeing some of these and some of these. Can I bring the coefficient and put it in the exponent? Yes.
Yes.
So is that equal to log 4?
Yeah.
Yes. Why should you leave it alone? Because some of you shook your head. And that's why you should leave it alone. If I'm not sure if it's legal, leave it alone. Because that's the answer you got. It's always safe to say, look, if the answer I got can't be simplified, just leave it alone. I don't have a quotient that I can reduce. I have a logarithm. I'm going to leave it alone. Yes, it is true that you could say this is 2 log squared. This is log 4. And one is really not considered better than the other because whatever you got first is probably the safest. But if you said log 4, that's correct. Okay? Now, I can't do that substitution on the first one because the degree difference isn't 1. So now when you look at the denominator, what do you think you need to see here? No, not the antiderivative formula, but what do you see physically? You see a 16 plus x of 4. You see a sum of squares. That's not your first priority. Looking at the degree difference should always be your first priority because that's more direct, it's easier, it's faster, you're done. The degree difference isn't 1. So the numerator can't be the derivative of the denominator. But the denominator looks like a sum of squares. So that's what I'm going to attack next. This is 4 squared plus
X squared squared.
x squared squared. Therefore, what's the only part of this problem that I can even consider as my u?
X squared.
The x squared. And is that the right thing up here?
Mm-hmm.
Yes. It's very subtle. But once you get the hang of things, you practice enough problems, you look at this one and you see it's of the form 1 over u du. You look at this one, you see it's going to be of this form. So now I'm going to do my substitution. I've got to do this step first. I don't want to do all of this in my head because it's not, to me, completely obvious. So I'm going to let u equal x squared. Du is going to be 2x dx. Do I have that? Yeah, I have more than I need. So if that's a 2, then what's in front? 4. Okay. I only have one more thing to do, and that's to figure out the new limits of integration. They will not be the same as the other problem, by the way. What are my new limits of integration?
0 to 4.
0 to 4. Okay, I left myself in a room here. So the new form of this integral is 4 times 0 to 4, 1 over 4 squared plus u squared. You don't have to write 4 squared. You could write 16. Why should you write 4 squared? Well, what's showing up at your answer, the 4 or the 16?
4.
4. That's why you should write 4 squared. If you write 16, what's the danger?
You might write
You
16.
might write 16 in your answer. Yeah. Do people do that? Oh, yes. Not the nice people, but there are people. Yeah. Those other folks we talked about before class, remember? You know what basketball team and hockey team those guys root for,
Mm.
right? Clippers, Ducks, yeah. Those guys do that kind of stuff. I hate to say it. It's not clearly obvious here. So what's the antiderivative here? Don't look at the coefficient, look at this first.
Oh.
1/4.
4.
Then u. Mm. Mm.
Don't do too much at one time. I will lose the coefficient if I do that. It's 4 times a fourth. I'm happy with that. Now, this is evaluated from, I know it's getting a little bit much, from 0 to 4. Ah, inverse tangent of 1/4 times 4. That's inverse tangent of 1. I'll just write it out. Inverse tan of 1 minus, what?
0.
Inverse tan of, all right, let's start with the easy one. Tangent of what angle is 0? 0. I like that one. The tangent of what angle is 1? Well, think degrees first if it helps. I don't know what this is. I'm blanking out. Go to your calculator. Put your calculator in degree mode. Put it in degree mode. Hit inverse tan of 1. And what does it say? It says 45. But your answer can't be a degree answer because a degree is not a measurement. A radian is a measurement. But if you don't know the answer, always use your calculator, put it in degree mode, and see, is my answer a common angle? Is it a 30? Is it a 45? Is it a 60? Is it a 90? Then it's really easy to convert to radians. What if it was inverse tan of 3 or something like that? Then you'd have some ugly answer, and you would actually leave it inverse tan of 3. That'd be the best answer. But inverse tan of 1 is 5 over 4. So my final answer is 5 over 4. Ooh. That's not bad, is it? Everybody okay with that? So that's the answer, 5 over 4. That's kind of nice. So we've looked at 4 problems where I paired them intentionally to put things that look similar next to them, because sometimes a substitution, like on the first two, sometimes it's obvious. I can't go wrong on that. I don't know what the answer is, but I know how to attack it. But when you get to the inverse trigs particularly, inverse trigs will either have a denominator that involves a sum of squares, or it will have a denominator that involves difference of squares. Okay? And that's not always obvious. Here. So now let's break it down to something smaller. I'll stick with 0 to 1. That'll work. Wow, this one looks crazy. Well, you only have one formula of the 20 that has a square root by itself in the denominator. Which one looks like that? There are 2 with square roots, but only one of them has only the square root, nothing else. Inverse sine. You don't have a formula for the cos. Remember, they're just the opposite signs. So inverse sine. Inverse secant has a root in the denominator, but it also has a function out here. Plus, in the inverse secant, the roles are reversed. So the a squared minus u squared under the root is the inverse sine. So right now, this is actually easier than any of the previous ones because there's nothing else that looks like this. So I just got to figure out what's my substitution. So I said that the denominator involves a difference of squares. So we need to identify what's actually being squared. So this would be 3 squared minus what? E to the x squared. Lest we forget, that's a rule of exponents there. That's where you would multiply the exponents. So if I let u equal e to the x, oh boy, this one always throws me. When the du is
E to the x.
oh, e to the x. Okay, maybe not. Yeah, that one we really should get. You know, what's interesting, and some of you hopefully noticed this on the last exam, when I asked you the integrals, one of the integrals asked is, what's the integral of e to the x? Do you know that 60% of the class skipped that one? That was the only one where the integrand was the answer. There wasn't any work to do whatsoever. Yeah, 60% of us actually skipped the integral of e to the x dx. The answer is e to the x. We just didn't do it. The second most skipped one was the integral of sine plus cosine. We skipped it. But the ones that were more challenging, you know, that you had to mess around with the exponents and, you know, you had roots. Everyone did those. But sometimes we go, oh yeah, that's right. I know this. This is not a tricky one. Limits of integration. As x goes from 0 to 1, u is going from, what's e to the 0?
1.
1. By the way, do we sometimes put a 0 there? Yeah, I'll have people at the highest level sometimes space out. E to the 0 is not 0. E to the 0 is 1. And then I have e to the first, which would be e. Oh, okay. So when I rewrite this, it's going to be 1 to e, 3 squared minus u squared under the root, Why? Because there's my du right there. I like this one. This one's friendly. Does inverse sine get the 3 in front? Inverse tangent, right? The 4 showed up in front. It's 1/4, but the 4 shows up in front in inverse tan. Does that 3 show up as a 1/3 in front for inverse sine? Are you sure? Yeah, inverse sine is the only one that it doesn't show up. It shows up for inverse tan and inverse secant, but not for inverse sine. So the antiderivative of this is inverse sine of 1/3 e to the u, I'm sorry, 1/3 u, sorry, from 1 to e. There's no coefficient in front because there's nothing going on here. So how do I write this? Well, e is a constant, correct? Could I write e over 3? Would that be legal?
Mm-hmm.
Yeah. Minus inverse sine of 1 over 3. Can I combine those into one inverse sine? No. Good one. Will some of us try? Oh, yes. No, leave it alone. And I say this kind of tongue in cheek. That is the answer. But sometimes we try to simplify things that can't be simplified. We go a step too far. Always ask yourself, if you aren't sure if it's legal, don't do it. The absolute worst thing that could happen is, oh, you stopped one step short. You know, now on your 40-point problem, you might lose a point. But if you actually change it to a wrong answer, you've kind of destroyed all the work because now that answer is not useful for anything. You know, you're in your physics class, you have the wrong answer. Everything that follows will now be incorrect. The ripple effect is huge. If you aren't sure, here's what happens. The best intentions. My final answer to the question is log 6 minus log 3, which of course is log 3. Right? Log of 6 minus 3, right? No. That's not the answer, is it? What is the answer? Not 6 minus 3, but 6 over 3.
That's that one too.
Oh, darn, I forgot what that log rule was. So you know what I should do? Nothing. And maybe I lose a point. But the other answer is completely wrong. And realistically, in any calculus situation, the numerical answer you got is not the end of the problem. It's probably what I'm going to use in the next step of the problem. And now I have a wrong numerical value, and I got to finish a physics problem or a chemistry problem. You use logarithms in chemistry? Yeah, this is the only part of algebra you use in chemistry. So if you're not sure, walk away. But if you are sure and you see an obvious simplification, take it. These cannot be combined, but sometimes people will try to combine them. If I'm not sure, leave it alone. In fact, in that case, I can't go any further. So the inverse trig ones tend to be a little trickier because, first of all, that integral right there was not hard to do once we recognized the form and we made the appropriate substitution. But is there anything that looks like that? Anything of your formulas? No. Your formulas don't look anything like that. You don't have e to the x's in denominators of formulas. But that was my u squared, and that was the whole point. Okay? Now let's try another one. Let's do something truly evil. Wow. This is different. You have a quotient and you have no exponents on the bottom. If this was a rational function, you'd be looking for degrees, correct? But why do you look for degrees? Why are we looking for the degree on the top to be 1 less than the degree on the bottom when it's a rational function?
Because it could be a derivative.
Because potentially it could be the derivative. But that was rational functions degrees. I don't have a rational function, but I do have a quotient. Is it possible my numerator is the derivative of the denominator?
Yeah.
Because that's really the same thing, isn't it? It's when you had a rational function, you had to look at degrees. There was actually more thinking involved. But here, my bottom involves a hyperbolic cosine. My numerator involves a hyperbolic sine, which is the derivative. I think pretty much this will work. What is going to be the form of this integration ultimately, do you think? It's going to be 1 over u du, exactly. And the moment you see that, I got a guarantee you're going to get it right, because you know exactly what the route is that you're going to travel. Now it's a domino effect. I'm going to write the next thing, the next thing, the next thing. It's going to flow. But if I don't see that, I got to the stop sign, the directions were a little smudged. I wasn't sure if I was supposed to go left, right, straight, or turn around. Right? I will misnavigate and I'll go in the wrong direction if I don't see that. So what is my substitution going to be?
9 minus cosh x.
Let u equal 9 minus the hyperbolic cosine of x. Then what's du?
Negative sine hx dx.
Do I have that? Almost exactly. In fact, let's do this. This is one I might rewrite just to make sure. Did I actually do anything, really? No, but now I have the form, my numerator is exactly the derivative of the denominator, so it's now of the form 1 over u du. Now I just have to concern myself with the limits of integration, okay? As x ranges from 0 to 2, the value of u will range from
8.
9 minus the hyperbolic cosine of 0. By the way, the hyperbolic cosine of 0 is the only one you actually do know. What is it?
1.
It's 1. How can I know that for sure? You have a hyperbolic key on your calculator. So go ahead and hyperbolic cosine of 1. That's the HYP cos 1. By the way, I'm sorry, what did I say? I'm sorry, hyperbolic cosine of 0. Sorry, I said 1. It's 1. Does it matter if I'm in radian or degree mode? I'm entering a 0. Doesn't matter. So that's going to be a 1. That's the only gimme. So what am I going to do for the other one?
9 minus cosine 2.
Yeah, 9 minus hyperbolic cosine of 2. Can I go to the exponential version of that? Can I go to the one involving the e to the x?
Sure.
Yes. Would there be any advantage to doing that? I want to remind you, because a lot of times that is not absolutely clear. I said the only time you are going to automatically change it to the exponential version is when your argument's a natural log.
Wouldn't the lower limit of u be 8 because it's 9 minus 1?
Yeah.
Oh, what did I write? I'm sorry.
1.
Where is it?
Very top of the whiteboard.
Oh, thank you. Yes, you're absolutely correct. You're absolutely. We said the hyperbolic cosine was 1. You're right. It's 9 minus. Good catch. So here we have an 8. I'm going to leave this way. I don't like that, but you know it's fine. If I really need a number, I'm going to my calculator. I'm in radian mode, and I'm going to go 9 minus hyperbolic, where is it? Hyperbolic cosine 2. And my calculator spits out an icky decimal, 5.2 something, 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 something. That would be a decimal equivalent of the actual value. So I can always do that, can't I? If I really needed a number, I can always do that. But I can't go from the decimal to work backwards. Remember, once you round off a decimal, you can never work backwards to say what thing did I round off in the first place. If I wanted to consider the exponential version, let's remind ourselves. Because there might be a situation where you say this is a better answer. Okay? We know this is true. So therefore, what is the hyperbolic cosine of 2? So instead of writing 9 minus the hyperbolic cosine of 2, could I have written 9 minus this? Yes. Does that present any advantage, though, in the long run? I'm never going to be able to manipulate this, simplify this. Nothing's going to go away. This is correct. I don't think it's better. No, I think that's a lot easier to use. And remember, you do have a calculator. If you really needed a decimal approximation, I think all of us would agree that I'd rather do that one on my calculator than all of this because they're equal. This is a lot more work. It is correct, but is it better? I don't think it is. So, -3 natural log absolute value of u. By the way, is it a good idea to determine if this is actually positive or negative? Do you think that might be wise? It's going into a natural log, remember? What if? What if that was a negative value? Well, how could it be negative? Make that a little bit bigger. Let me make that a 3. If I make that a 3, this is now a negative value. Oh, and if that was a negative value, then that absolute value comes into play, doesn't it? But right now, that is a positive value. So as ugly as this is, the answer was not that hard to actually state. So my answer is -3 times natural log 9 minus natural log of this yucky quantity here. Can I distribute the -3? Sure. Can I leave it alone? Sure. Nothing's going to combine, nothing's going to cancel. I have the difference of logs. Can I write this as the log of a quotient?
Mm-hmm.
Sorry, that's an 8. I keep writing 9. Can I write this as log of a quotient? Yes. That's going to be pretty ugly, isn't it? I don't think I want to write the log of 8 divided by this. It's correct, but I think it's just way too messy. Now, I probably, I look at that, I weigh that as I'm walking away. This problem, the numerical value of this problem is terrible, but the actual calculus of this problem was not. That just wasn't that bad.
Are they supposed to be flipped?
Yeah.
It's the lower value.
What did I do? Oh, you know what, I'm sorry. I thought yeah, no, you're right. I had the negative, No, you're right. So it's log of, sorry about that, 9 minus cos 2. In my addled brain, I was now thinking, now because that's a negative, and I didn't do it anyway, so it doesn't matter. I was going to say, a lot of us would want to switch the order because I have the negative on a subtraction. Does anybody like a final answer that looks like this? Because what's this the same as? Yeah, I was actually doing that in my head and I tripped. I missed a step. Yeah, so I was thinking 3 times, but I left the negative. Could I write this as 3 times and then switch the order? Sure. Is there any advantage? I don't know. All versions of this are fine because you can't simplify this any further, so just leave it alone. If I'm in physics or chemistry, is that the last thing I wrote? I'm probably giving an ugly decimal, aren't I? So now does it really matter how I wrote that, as long as I get the decimal correct? Yeah, because in a physics class, maybe this represents work done, maybe this represents speed, maybe this represents the force applied given the units, things like that. Chemistry, it might be how much milliliters of solution I need. All of these things are correct. But in those cases, you probably give a decimal answer. All right, let's do some more easy ones here. Okay, let's do. It's relatively simple. Yeah, this is. Is the u the tangent, or is u going to be the x squared?
X squared.
How do you decide?
Because there's not a derivative of tangent in the.
Okay, that's a good one. There's not a derivative of tangent sitting around. But mostly because my argument isn't an x, it's a function of x. So it's probably safer to go inside the tangent and say, you know what, that's the most likely culprit. And now, as Chase has pointed out, I have a chain rule factor sitting there right next to me. If I don't have this x here, this is horrible. Or if that x is raised to a different power, this is horrible, because we recognize it pretty much has to be the chain rule factor. But again, I'm looking at degree difference. It's the right degree difference. I may not have the right coefficient, but that's the easiest part of the problem to remedy. So let u equal
X squared.
X squared, du equals
2x dx.
2x dx. I'll fix that first. Now, some folks would say, no, you have to rewrite it and put it right there. I just did. Everybody see that? I just rewrote it and put it right there. Don't physically rewrite it. It's not wrong. It's just overkill. As long as you see you have your chain rule factor exactly, and I just moved it right there. I'm not going to cross it off and rewrite it. Now, the part that gives us the most trouble, but is actually the simplest part, the new limits of integration. I don't know why this would ever give anybody trouble, because this isn't even algebra. This is arithmetic. That's all it is. And it's never going to be complicated arithmetic, but we're going to forget to do it occasionally. So, when x is 1, what's the value of u?
1.
All right, didn't mess that up. When x is root 2, what's the value of u? 2. I think I like this one. Do we have an antiderivative formula for this? Yes, this showed up on a recent quiz, and again, a significant number of people went and re-derived the formula. By the way, I'm sitting down for the exam. I made my formula card, and I wrote 19 of the 20 antiderivative formulas on there. Guess which one I forgot to write down? So then what can I do? Remember, fourth rule of life? All else fails. Change it to sines and cosines and re-derive it. I don't want you to do that, but you know how to do that. No, we have an antiderivative formula. You don't have to re-derive it every time you use it, but if you forgot it, this one's not that bad, because it is sine over cosine. Right? It ultimately is going to be a log of something, you know that. But it's better if I just remember the antiderivative formula. So it's 1/2 log absolute value of what?
1 secant.
From 1 to 2. I will make the assumption that you do not know every single possible value a trig function can take on, but you have the ability on your calculator to always do things. Am I right? So, first of all, your calculator needs to be in radian mode right now if I was going to do a calculation, because the answer is always a radian answer. So I'm going to go 1/2 times log of the secant of 2. I don't know if that's positive or negative yet, so I'm going to leave it like that. Minus the log of the secant of 1. I don't know if that's positive or negative. And here's what I mean. Pi is a little bit more than 3, agreed? So what quadrant would I be in if I was 3 radians? If pi is a little more than 3 radians, and you're exactly 3 radians,
You'd be in the second.
good. I hate using common sense and calculus in the same sentence, but that's pi radians, so 3 radians is probably closer to there. I'm in the second quadrant. Secant, which is the reciprocal of cosine, is what sign? What SIGN? It's negative. What does that mean? That means that's negative. So I need to leave the absolute value on. Pi over 2 is a little more than 1.5 radians. So where would 1 radian be?
The first.
Well, I said 2 radians is still second quadrant. So is secant 1 positive or negative?
Negative.
You just said first quadrant.
Oh, I said second.
So this one would be first quadrant, this one would be second quadrant. Now, I'm not sure, I just answered the question. I need to leave the absolute value on the first one. Can I just leave it on both then?
Yeah.
Sure. Absolutely correct. Now, I would like a numerical value for these. I'm in physics class. And although this is the answer to the question, is that going to help you when I said, what's the impact speed when the rock hits the ground? And you said, it's half log of absolute value secant to my... You're correct. I have no idea what that means. It might be like, so you got the bill at the restaurant, and they put the bill in this form. That would be weird, I know. But do you have any idea of the value of that number? Probably not. So how do you do that on your calculator? Well, isn't secant the reciprocal of cosine?
Yeah.
So can I just do the cosine and take it, you have a reciprocal key, the 1 over x key. Don't take the reciprocal of the logarithm. Take the reciprocal of the cosine. Now, if you were doing this on Desmos or something, do you need to do anything weird? No, you have these functions. But on your calculator, it's intentionally limited. Do you notice the inverses too? You don't seem to have all the inverses, but you know how to manipulate and get around it. I would like somebody to give me a numerical value for this.
0.1305.
Okay, so give me 1 second. So log. Oops, hold on a second. Yeah. There we go. All right, so what did you get?
0.1305.
Does anybody else get that? Did you have the 1/2 in front?
Yep.
Does anybody else get that? I don't think I got the same thing. Oh, you know what? I may have just hit the wrong button. Okay, hold on. Try one more time. There we go. You got, say again now?
0.1305.
Yeah. I kept hitting the wrong button. I kept getting error.
Hmm.
Does anybody get 0.13? Yeah, this one here is very tricky. I don't, by the way, I just did this on my cheap calculator, but I had to really be clever, and I have backdoors and I have it rewired and stuff. If I was going to do this, and I actually had to do this calculation, I'd be far more likely to actually just go to Desmos or someplace where I can enter the secant buttons. But here's one of the problems all of you are facing when you're doing this on your calculator. Your calculator doesn't have an absolute value key,
Mine doesn't have a secant key.
but you have a cosine key. So you
I got
flip
an
over.
absolute value, but no.
Oh, you have, okay. The
Yeah.
problem a lot of us have is what do we do about the absolute value? So one way you can do it is you can actually do this calculation, and it's now negative. Then you can simply change its sign before you move on. Does everybody understand? Calculate the secant of 2, it's going to be a negative number. Change it to the positive sign. How do you do that? We multiply it by -1. Now take the log of that and now move on. That is one way to do the problem. That's probably the easier way to do the problem. Does that make sense? So there are some tricky ways, or that is the answer, but like I said, you're in a physics class or a chemistry class where they actually want the decimal value, and you're going, I don't have these keys on my calculator. You don't have a secant key, and most of you don't have an absolute value. Ooh. So how would I do that calculation? So there's a couple of clever ways to do it. I don't need you to be clever, because that's the answer. You can stop. Okay? Let's see. We can get a little bit more. Okay, how about, let's do, well, again, I'm looking at my sheet of formulas. There's no formula that looks like this. But there's one formula that kind of looks a little like this.
Secant inverse.
Inverse secant looks a little like this, doesn't it? It's not exactly like this.
Missing the absolute value, but
Well, no, because secant inverse, no, it's not that, that's the derivative, but secant inverse, that's a u squared and that's a u.
mhm.
If that's u squared, that's definitely not u, is it?
Mm.
Might be someone else. So, how do I do this? Well, you're right when you say inverse secant is the only thing it could be, if it's even possible. So I'm going to attack it from that point of view. I see a difference of squares here. What do you see?
X to the fourth squared. Minus 4.
The 4 is irrelevant. That's just showing up in the answer. I'm not worried about that. It's the x to the 4th. I only have one choice for my substitution, then what is it? Let u equal x to the 4th. Then du must be 4x cubed dx. I can't do this one yet because I need a 4x cubed in the numerator. I don't have anything in the numerator. And not only that, if my u is x to the 4th, don't I need an x to the 4th right here? So I need an x cubed in the numerator and I need an x to the 4th in the denominator. How the heck is that supposed to happen?
X cubed over x cubed.
Oh, that's a pretty good idea. So Max says, what if I do this? Algebraically, would that get the job done?
Mm.
Yes. Is it legal?
Mhm.
You can never multiply or divide by anything that can potentially equal
0.
0.
But the limit's 2 to 3.
It's not only that, look at this. Can this x equal 0? No, because that would give you an imaginary number. So this x has to be, you know, I think square root of 2 to the 8th power would be 16. So this x has to be bigger than the square root of 2, in other words. That's why this is okay. Oh, so x can't be 0 anyway. Therefore, is this a legal move? Yes. If x could in fact be 0, then we get in trouble with that one. But x can't be 0. X got to be something bigger than 0. So we're good. Well, but I need a 4x cubed. How about if I do that? Like that? Max is giving me the thumbs up, and well, I trust Max. It's probably a bad idea, but I trust it. So the form of my integral is now 1/4. Let's write it out. I've got x to the 4th, x to the 8th minus 16, which is this. So I technically have u squared minus 4 squared. It now looks like this, which is exactly the form of inverse secant. Now I need to figure out what are my limits of integration. So as x ranges from 2 to 3, the value of u will range from 2 to the 4th to 3 to the 4th, which would be what?
16 to 81.
16 to 81. Should this be simple at this point?
Mm.
Yeah, here's the part where some of us get in trouble. This is exactly the form of the antiderivative I have on the sheet of integral formulas, meaning I don't have to do anything. The next thing I write should be the antiderivative. I don't have to do anything at this point because the sheet says 1 over u squared minus a squared. And that's exactly what this looks like. Now, how many times does the 4 show up in this answer? 2 times. Inverse tan and inverse secant, you get it in front and inside. Inverse sine is the one you don't. And that always throws people, because 2 of the 3 inverse trigs. So this answer, don't look at that yet. Just right here, I'm going to get 1/4, oops, not inverse sine, inverse secant, 1/4 u from 16 to 81. What about this 1/4? It's going along for the ride. So I have a 1/4 twice. Okay? Yes? So far? All right. So my answer is 1/16 inverse secant of 81/4 minus inverse secant of 16/4, which is, what's 16/4?
4.
for the sine, cosine, tangent, whatever, of an angle produces a ratio. The inverse trig function of a ratio produces an angle. So we're asking the question, is 81 over 4 or 4 a common ratio we see with secant? I don't know secant that well. Okay, then it'd be the same as me asking, is 1/4 or 4 over 81 a common ratio we would see with cosine? What do you see with cosines? You see a half, root 3 over 2, root 2 over 2. Do you see anything with 81s in it or fourths in it? What do you think, yes or no? No? So therefore, is this going to produce a common angle?
No.
No. So walk away. In other words, I can't do better than that. That's the best I can do. Everybody cool with that? It's ugly. But answers don't always have to be pretty. Okay? If you need a numerical value, you can always use a calculator. If you're saying my calculator, I don't know how to do an inverse secant on my calculator, then you can use higher form of technology, because in a math class, you're never going to have to get any numerical value for this, but you will in your science class perhaps, which means they're probably expecting you're going to go somewhere, you know, there's a lot of places you can go to do the calculator, but it's or to do the calculation, but it's probably not your calculator. Again, it's limited in a lot of things. Okay? Question? All right, we've been practicing for 2 days now of just straight out integrating and then integrating with substitution. You don't substitute on all integrals. If you can integrate directly because what you have, it's really simple to integrate, then you do. If what you have does not look exactly like an antiderivative formula, then it's likely you have to use a U substitution, which means you have to have the chain rule factor or at least a scalar multiple of the chain rule factor to proceed. But the main thing is, if it's a definite integral, and you change the variable, you do not change back later. You change the limits. Now, is it possible I can do these problems without ever physically changing the limits? Yes, I showed you the very first problem, but that problem is twice as long. That's the problem where I do the general antiderivative all the way to the end, get the answer. Now come back and take that answer and then finish this all the way to the end. It's at least twice as many steps, and you're not benefiting because you're going to get the same numerical answer in the end. It's just going to take you twice as long to get there. It is good to know how to do that problem down the road. Now, the other thing is, down the road, you may not have to physically change things because you'll, not this problem, this is a lousy example, but there'll be problems where the substitution is simple enough that you can see it. You can see it's right in front of you, and you don't have to really do anything. I'm going to give you an example. It's not what we're going to do in this class, but it's what you're going to do down the road, because through repetition, you've just gotten really good at things. Is my numerator exactly the derivative of my denominator? Yes or no? Mm-hmm. So we would say let u equal x squared plus 1, let du be 2x, and I rewrite this as 1 over u, then I integrate it, I get natural log of absolute value, then I substitute back. Is that obvious? You just told me the numerator is the derivative of the denominator, then that is the answer. Why am I not using absolute values?
Because that can never be negative.
Can it be this simple? This was a U substitution. And I did do the substitution. I said let u equal x squared plus 1, and then du is 2x dx. What didn't I do?
Everything in between.
I didn't rewrite it. Now, this class I want you to write it because you're going to get lost. It's too much to try to do this. I don't want you to do this in your head. But next semester, I do want you to do this in your head, because you will have had enough practice that this will be simple. Why can't I do this now? Because there's too many variations of the problems. It's too hard to look at a problem and go that far ahead. I don't need anybody to see exactly what the answer to this is in the end. Now, you want to do the substitution, but after a while, this is one I'm talking about where there was nothing for me to do. This was slam dunk. There will be a point, like in my Calc 3 class, I'm almost annoyed if they physically do this as a substitution, because they can all see there's the derivative on top. That's the antiderivative. Just go directly. but they've also been doing this for 3 semesters. That's the difference. They've literally done thousands of problems at that point. We've done, tens of problems maybe less. There will be a point when I want you to do this. I don't need you to do this now. So right now I'm actually asking you, demonstrate the substitution because I want you to get really good at it. Because there will be problems that you can't do in here. Most of the problems you will not be able to do that easily. And you have to have a method that is flawless and works. Okay? I've taught math for a long time, and I have taught many very brilliant students. I remember I taught high school a number of years ago. I taught high school in the day, and then I came here and teach in the evening, and I liked this better. So I chose this full time. That was a long time ago. But I would teach the honors classes, like the accelerated geometry. I'd get the really smart kids. But I had kids that had no work ethics in some cases, not all. And I probably the smartest kid in the entire school, he was a sophomore in my geometry class. Everything came easy to him. And I would try to encourage him to explain his answers, to represent his work. He's like, why? But I can do everything in my head. I said, there's going to become a point when you can't do it in your head anymore. Everybody's going to at some point get to the point where they can't do it in their head. And I said, you have no technique. He didn't graduate. He didn't pass a class his senior year. He never learned how to do any form of studying. He had no work habits. He got an A in geometry, got a C the following semester, and then failed every class his senior year because he not only didn't do homework, he was now at the bottom of every single class because he had no work habits, no work ethics, and he couldn't get answers right anymore because he couldn't do them in his head anymore. He had problems that involved calculators. He refused to even buy a calculator. This was at a wealthy private school. He didn't graduate from high school. The sad thing was, both of his parents were professors over at UCSD. It didn't go particularly well. But he tried to get by on sheer talent alone. That'd be kind of like saying, you're playing basketball in a league of 10-year-olds, and you are dominating. Right now, you're dominating the league of 10-year-olds. You haven't been challenged yet. What happens when, and that's all you ever do. And now you're going to play against a bunch of grown-ups, and what's going to happen? Probably not going to go well, so therefore you're going to quit playing basketball. That's kind of the same analogy. You've got to get good all the way through before you can start taking the shortcuts, okay? Because if you take the shortcuts too soon, you won't get the method down. I need you to have a flawless method. Then every now and then you'll say, I know how to do this problem. That one's a gimme. That's what I want you to see. Because you already know how to do everything, okay? Let's go ahead and stop it. I'll do the roll thing. We're going to... Okay, we're going to start something slightly different. This is an application.
If you acted less
We're going to go backwards a little bit to when we first did the Riemann sum, and I mentioned before there's another way we can do an area estimation. So I've got a situation here. Keep it simple. I've got y equal f of x from a to b. Now, what we did with the Riemann sums was we split this up into random width rectangles, chose any place within the interval to square it off, and we said the area of those rectangles is a loose estimation and actually can be a very good estimation, okay? But what if instead of rectangles we used a different shape? So here's what I want to do. I want to subdivide this one evenly again. I want all my delta x's to be exactly the same. Okay, so when I split this up, let's say I'm going to go this far. Now let's pretend all my delta x's are exactly the same. But instead of rectangles, I just simply want to connect endpoints. What are those shapes? We mentioned this last tape.
Trapezoids.
Those are trapezoids, okay? Now, do we know the area of a trapezoid?
Mm-hmm.
Let's do this off to the side because the trapezoid is actually a fairly simple shape, but those don't look like trapezoids. Well, they are, but they're all sideways. So in baby algebra, hopefully you learned this. Let's call this base 1, base 2, and the height would be from here to here. I don't need these lengths. Okay, so I derived this. It's a very simple derivation in a baby algebra class, and I'll show you so you don't have to just trust. If I take the midpoint from here and I connect it to the midpoint from here, that's called the median. If I then said, let's make a rectangle. Oh, hold on. It's probably Poe. Yeah, I think it's Poe.
Yeah, typical Poe.
I got here from Poe at least a couple times a day. All right. Now, do you think the area of that rectangle is the same as the area of the parallelogram? Excuse me, the trapezoid? Namely, look at that triangle and that triangle. They are actually congruent. That triangle and that triangle, they are actually congruent. So the area of the trapezoid is equal to the area of the rectangle, which would technically be the length of the median times the height. But how the heck am I supposed to find the length of the median? Oh, wait a minute. The amount that I cut off here is exactly the amount I added here. You got 80 on one test, you got 100 on the next test. If I take 10 points off the 100 and I add it to the 80, that puts me at 90. That's exactly what I just did. Another name for that is the, starts with an A.
Average.
This is the average. Yeah, it's the average. Oh, the red is just the average of the blues, isn't it? And what's the average of B1 and B2? Half B1 plus B2
times.
times the height. That's the area of the trapezoid. That's where it came from. You all saw this as kids. You probably didn't remember it. And now you go, oh, it makes perfect sense. It's the average of the bases times the height. So could I fairly easily find all of these areas? Yeah, these are all geometric shapes. There's no calculus involved. In fact, makes it even easier. Let's call this x0, x1, and so on. All the way down, this is xn. But like we did the first time, right? When I used the summation formulas, when we made all of our delta x's of equal width, we said, well, the delta x's, they're all the same. They're all going to be the same thing. It's going to be the width of the interval divided by the number of partitions. So I'm going to erase the I because they're all the same. I'm using the same delta x across the board, like we did in the very first problem that we did with summations. Okay, you with me so far? So if x0 is A, then what's x1?
A plus 1.
It would be A plus delta x. Oh, what's x2? And so on. All the way down to xn would be A plus n delta x's, which would be A plus n times B minus A over n, which is just B. I would just add all the way across. But this makes it really easy. We're not taking a limit this time. We are actually going to count a finite number of trapezoids. Now here's the interesting part of this. I can do this not necessarily as a limit problem, but I could do this as a simple computer program. And I'll show you how, because actually people do this as a computer program. I want to add up each of these areas. So let's call the first one, I don't know, how about A1, A2, all the way down to AN. Okay? Well, let me, A1. It's the average of the bases, but wouldn't the bases technically be these two heights? Because it's on its side. And what would the height be?
Delta x.
Delta x. Remember, it's a trapezoid on its side, so here's the two parallel bases, and the height would be delta x. So if you want to draw it this way, go ahead and draw it like this, right? There's my delta x. If I tilt this back up, that's f of x0 and that's f of x1, right? That height is f of x0, that height is f of x1. So what's the first area? It's going to be what?
Half
One
f
half.
of x0 plus f of x1 times delta x.
Beautiful. That's my first area. Is there any calculus in that step? No, gosh. All I got to know is what's my function and what's n. And n is given. Just so you know, we generally use small values for n. Maybe 6, 8. I don't need n to be large. If I wanted a more accurate estimation, I would make n large. Maybe I would make n 100 or 1,000 or 1,000,000. Not a limit, just really thin delta x's, and then I would just do that on a computer. That would be, again, a basic do loop. And we just add them up. It actually isn't very hard. Anybody with basic programming skills, this is a fairly simple thing to write. I don't need you to do this. But I'm telling you, you could get more and more accuracy by having skinnier delta x's. Am I going to have a little bit of over-under with these line segments? Yeah. But the skinnier the delta x is, the less over and under. In other words, the closer to actual value without even having to take a limit. So what's A2? Well, then that would be 1/2 of f of x1 plus f of x2 times delta x. Agreed?
Hmm.
And I'm going to keep going all the way down to the last one, which would be 1/2 of f of x n minus 1, the second to last one, plus f of xn times delta x. Now, let's suppose that n isn't outrageously large, because we're going to do this by hand in a moment with a cheap calculator. Most of the time, like I said in the textbooks, the n's they'll use is 4, 6, 8, that's about it. Because you get the point across without having to be large. But that's a lot of individual calculations. What if I added all these up? Do you think there's maybe some factoring and some shortcuts that could take place? If I add these up, now think about this for a moment. I'm going to add up this area to this area to this area to this area and so on. So in my first trapezoid, I am using that height. And in my second trapezoid, aren't I also using that height a second time? And then I'm using this height. But in the next trapezoid, I'm using this twice. Does everyone see that all these heights are going to get used twice? All of the heights are going to get used twice except for which ones?
The first and the last.
The first and the last. Does everybody see that? So, I'm not a rocket scientist, but you know, I play one on TV. If I add all these up, I can say if I add up all the f of x's, I'm going to have f of x 0, and you just said I'm going to have 2 times the next one, and 2 times the one after that, all the way down to the second to last one, and then only 1 times the last one. Because the last height and the very first height are only going to show up in one trapezoid. Every other height's going to show up in 2 trapezoids. What else is common to every term? 1/2 and delta x. What we're going to see is, even with small values of n, this is a really incredible estimator. It's never going to be equal because we're never going to take a limit. We're just going to do the calculation. Now here's the first rule of thumb. You would never do this if you knew how to find the area under the curve. So what is this an estimation of? This is an estimation of the integral from a to b of f of x dx. So here's the way I want you to think about this. I'm going to give you a function. I want to find the area under the curve, but we do not know how to integrate that function. We don't have an antiderivative for that function. We haven't learned how to do it. Maybe it's not something we've learned yet, or maybe that function actually can't be integrated. So what are you talking about? For every function that you know how to do, for those basic 20, there's an infinite number of variations of the same thing that cannot be integrated. Meaning there are far more problems that can't be integrated that can. We only learn how to do the ones we can. We learn how to estimate or do other things for the ones we can't. So let's make the simple assumption that we actually can't do this. Then this would be an estimator of this. It's not the best and it's not the only, it's the simplest one because there's no calculus. So we have a really clever name. I am estimating the area under a curve using what shape?
Trapezoid.
Trapezoids.
Trapezoid's real.
Yeah, it's like I said, we are so clever. This is called the trapezoid rule. Remember, what's the rule for taking derivatives of products? Product rule, yeah. The most important formula may be before calculus, the one involving a point and a slope. The point slope formula. Yeah, it's kind of sad that we haven't come up with more clever names than that, but this is called the trapezoid rule. So we're going to do a problem. I'm going to walk you from beginning to end. There's no part of this process that is difficult. It can be a little tedious, and all you need is a cheap calculator. Okay? Now, there are problems out there, and I think you should all do this when you're at home. If you know how to use Wolfram, Wolfram is beautiful. I'm doing the whole problem from beginning to end. I'm going to give a decimal answer to the problem. I don't know what the answer is. I'm giving a decimal, and I'm hoping I did the problem right. Could I have totally bombed it and messed it up? Yeah, because I don't know what I'm supposed to get. I can then go to Wolfram and have Wolfram numerically calculate the same integral, and it'll give me a long decimal answer. Is my answer going to be the same as that answer? No, not possible. You're doing an estimation. But should your answer be really close to that answer? Yes. Do you remember when we did the tangent line estimations? You guys remember doing that? We did a really simple estimation. We said, what's the value on the tangent line? We used it to estimate the value on the curve, and they were really close. That's how we knew we did it right. They were not equal because the tangent line left the curve. These can't be equal because you can see over and under. But our hope is that it's really close, and I get really close with only doing a few terms. That's the power of this. Okay, so let's do an example of this. And it's just a straight up formula that's easy to use. All right, so here's what we want to do. I'm going to write it this way. We want to use trapezoid rule to estimate, I'll do a simple one. The integral from, how about, I don't know, 1 to, don't go too big. Let's say 1 to 4 of the square root of x squared plus 1 dx with n equal to 6. We're going to do 6 trapezoids. What I'm going to do when we're done with this problem is I'm going to go to the internet, I'm going to go to Wolfram, I'm going to calculate the value. I'm cheating a little bit in that you cannot integrate that today. That is a technique you're going to learn next semester to actually be able to integrate that. You will be able to integrate that specific function next semester. But in general, we don't know how to integrate this, so the best we can do is to use the trapezoid rule. So we're going to break down the problem, we're going to write down all the pieces we need, and then we're going to break out our calculators. Let's start with the delta x. What's my value I'm going to use for delta x?
3 over 2.
3 over 6.
How about 4 minus 1 over 6? Everybody okay with that? My interval is from 1 to 4, so I have the width of my interval divided by n, so that's going to be 1/2. So when I write down my formula, coincidentally there's a 1/2 here. There's a 1/2 here because we factored it out, and we just did a delta x of 1/2. That only had to do with how big my n was. I could have done it differently. I like using simpler values. So the next thing I need to do is figure out what values of x am I actually going to use. So my x0 is 1. What's my last x going to be called? x6. What am I going to count by? So what's x1?
1/2.
Well, how about 3/2? Because I got to stick it into a formula. So x2, x3, add a half.
5/2.
x4, x5,
7.5.
and x6, 4. Am I done? Yeah, because we said from 1 to 4. I need these values because these are the values I'm going to put into the function. By the way, what is my f of x in this problem? That's f of x. That's the thing I'm integrating. So I now need, what is f of 1? What is f of 3/2? What is f of 2? What is f of 5/2? What is f of 3? What is f of 7/2? And finally, what is f of 4? Do not give me decimal values for these. No. Just give me the square roots. Okay? By the way, you don't have to simplify anything, but sometimes you can simplify a root and it makes it easier to enter into the calculator later. So what's f of 1? is root 2. What's f of 2? Now there's two ways you can do this. I'm going to have 3/2 squared plus 1. Agreed? That's what's going under the root. Well, that would be 9/4 plus 1, which is 13/4. Therefore, the root of this is the root of 13/4, which would be 1/2 root 13. That's absolutely correct. What's 13/4 as a decimal?
3.25.
3.25. Could I also do this? In the end, does it make any difference? No, because in the end, I'm going to add them all up and hit equals on my calculator anyway. If you have to do an approximation within the root, within the problem, then leave it as a fraction. So my next step, I'm either going to use this number or I'm going to use this number. It doesn't matter because they're exactly the same thing. Which one do you want to use? The decimal under the root or 1/2 root 13? Okay, we'll go with the decimal under the root. F of 2? 5. F of 3? I'm sorry, f of 5/2, not f of 3.
7.25.
Square root of 7.25. F of 3. F of 7/2. One of the reasons, by the way, one of the reasons I'm a big fan of doing this one is because when I put it in there, all those values get doubled. And then the half goes away and I have an integer under a root. I'm a fan of using the half of the root of an integer because it's easier to enter an integer in the root than it is a decimal. But it doesn't make any difference. It won't change your answer. So what's this one?
1/2 root 53.
Well, let's be consistent. If we're going to do this, we'll do it all the way down. You guys have calculators. 13.25. And finally, what's f of 4? Square root of 17. That should not present a challenge. It wouldn't matter what my integrand is. I always start by finding the delta x, figuring out my first and last value. Why? Because I need to know what I'm plugging into my function. Then I take each of these values, I put it into the function. Don't approximate these. No, no, no. Only at the end do we even need to use our calculator. So the next piece of the puzzle is I'm not actually going to do this. Okay? We write it like this. We say that this, well actually, sorry, let me write this specific, not f of x. Now the formula is 1/2 of f of, that's my x0, that's the first one. So that one shows up once, that one shows up once. So I'm going to write root 2 plus 2 times root 3.25 plus 2 times root 5 plus 2 times root 7.25 plus 2 times root 10 plus 2 times root 13.25 plus just the last one now, root 17, and the whole thing was times 1/2. Now, let's everyone do this on your calculator for me. Enter the roots. A common error that people do, and I've never quite figured this one out, this is just silly. I'm going to calculate this, write it down, and then I'm going to re-enter the rounded off number, and then I'm going to calculate everything a second time. Why in the world would you do that? You just did everything twice, and no matter what, your last decimal place is going to be off. No, just do that whole thing from left to right, hit equals. And look at your entire screen at that point. Okay, tell me when you got a number, anybody? Hopefully we all get the same number.
8.15, 16.3.
Did you,
Oh. Shit.
you know, I cleverly recognize your answer was exactly twice as big as his. 8.15, is that what you guys are getting? Okay, so how do I say that? This part here, by the way, I just approximated this and you said this is approximately 8.115? Okay, I don't really care how many decimals you go, that's fine. Does that mean that that's the approximation to this? No, that's the approximation to what I just hit in my calculator. So the best way I can answer the question is to actually write it like this, just so you know. I'm doing an estimation of this integral, and my estimation is 8.15. Does that mean the integral equals 8.15?
No.
No, that's what the sum of the areas of the trapezoids is. Okay? Now, I'm only going to do this for this problem, if this operates. There we go. Okay, I'm a big fan of Wolfram because it's a really nice, handy check. By the way, I just went to Wolfram and it's doing a numerical calculation, but I told you technically we'll be able to learn how to integrate this next semester. Wolfram's giving us 4 decimal places. What does it say? 8.1458. By the way, can anybody give me more decimals than this? Does anybody still have it on the screen?
8.1512.
1512?
Yeah.
How far are we off? If I'm looking at 4 places, we're off by about 0.0054. Is that pretty close? How could I improve upon this? Do you want to do this by hand if I said, let's go from 6 to 60? No, but this is, again, anybody who's ever written any computer code, even the most simplest level, you understand a do loop. Oh, okay, so now I'm going to make my delta x instead of 1/2, I'll make it 1/20. And then I'll say my x0 is 1, and then the next one add a 20th, and then keep adding a 20th, and then do the calculation. It's not very hard. I don't want anybody to do this unless you actually have programming skill. But to write a computer program to do this entire problem would then be calculated in a split second once you ran it. Would our answer be closer? Yeah. It would probably agree to at least the first couple places. Did we do any calculus whatsoever in this problem? No. We only did 6 trapezoids. Think about that. That is very, very powerful, that we got an answer that close with only doing 6 trapezoids. So the trapezoid rule is very powerful, but it's not flawless. And here's where the trapezoid rule, can actually, I'll write over here. It can be less accurate. There's a second rule you're going to learn. It can be less accurate. If I had a curve, all over the map, and I'm doing my trapezoids, If I had a curve that was wildly changing and I picked an arbitrary number of trapezoids, could I end up doing this kind of thing? You see what I'm getting at? Is this going to be very accurate? No, because my curve is moving too fast. But what if I have a curve that is really slow moving? It's not straight, but it's... my trapezoids are going to be unbelievably accurate. That doesn't move real fast. So if your curve is not changing rapidly, doesn't matter if it's concave up or concave down, it's just not changing very rapidly, the trapezoid rule is going to be really, really, really close. But if my curve is changing wildly, the trapezoid rule is not as accurate. So there's a second rule we learn. Okay? Where, let me do the wildly changing one. Where instead of trapezoids, strangely enough, we use parabolas, which is kind of interesting. If I have a curve that is rapidly changing, turns out if I use parabolas, that actually gives me tremendous, or I should say greater accuracy. The formula is a little more complicated. It's in every calculus book. You basically then calculate one of the trapezoids. It has 3 pieces. And then we add it to the next one, which has 3 pieces, and the next one has 3 pieces. And it ends up the coefficients using the same x0, x1, x2 that we did before. It ends up looking like this. The first trapezoid looks like f of x0 plus 4f of x1 plus f of x0 times a third. The third is when if I thought about the area under a parabola, think integration for a moment. You're integrating x squared, so you have 1/3, okay? So the 1/3 in front comes from the integration of an x squared. But then when we evaluate it, this is the area of the first one times the delta x. That's the first parabola. But then when we do the second parabola, we start, I'm sorry, that should be a 2. Then the second parabola, I'm not going to go through the whole derivation because it's quite a bit longer. And we do this all the way down the line until we get to the last one, which would look like this. F of x n minus 2 plus 4 times f of x n minus 1 plus f of x n. Now, this looks kind of complicated. The only absolute rule in this situation is my n has to be an even number, because I have to have this even number of pieces each time. With the trapezoid rule, n can be anything, but we typically use small numbers. This one here, where I'm using parabolas, n just has to be even. So when I add all this up, this looks really crazy wild, except that I noticed, just like before, this guy shows up exactly once. This guy shows up exactly once. Every term has a delta x. Every term has a 1/3. So you with me? You know what? I don't need this because I'm going to do the same problem. We already know what the answer is now. Hopefully you guys have it written down. You've memorized it. Okay, so if I add these guys up, our next one looks like this. It's 1/3 f of x0. And when I add these up, do you notice that the f of x2 happens 2 times? I'm sorry, the next one's f of x1. It happens 4 times. Sorry about that. Then f of x2 happens 2 times, doesn't it? Now what about f of x3? 4 times. And do you notice anything about the coefficients? Then the next one is going to be f of x4 starting over, so it's going to happen 2 times. Do you notice anything about the even? Evens are going to happen 2 times, but the odd ones are going to happen 4 times. I said n had to be an even number, so n minus 1 would be an odd number. So I'm going to have an alternating pattern here, aren't I? Where that was 1 and then all 2s and then 1, this is going to go 1, 4, 2, 4, 2, 4, 2, 4, 2. Eventually, the second to last one is going to be back to a 4 and then back to a 1. 1, 4, 1 added to 1, 4. We just have to restart. Hopefully that's not the battery giving us a problem. So can everyone see the alternating pattern then? 1, 4, 1, 4, 1, that kind of thing. And then on the outside, delta x. So what I would like to do is do the exact same calculation, but using this formula. And I think what you're going to find is this one might lead you even slightly closer. Okay, so everybody get out your calculator. What am I going to do? So for the next one, I'll just write it right underneath. I'm going to go √2 plus 4 of these, plus 2 of these, plus 4 of these, plus 2 of these, plus 4 of these, plus the last one, and the other difference is it's going to start with a 1/3. You don't generally do both at the same time. You do one or the other, because you're going to get an answer that's really, really similar. So I'd like everyone to do this from beginning to end on your, again, cheap calculator's all you need. And let's go 4 places on this one so we have something to compare it to. Okay, tell me when you have a number.
8.1459.
Okay, do we have agreement on that one? Chase says he got 8.1459.
59.
I've logged off. What was the original, what was the Wolfram number? Did anybody write it down?
8.1458, I think it was.
Was it actually 1458?
I think so.
8.
Would you say this is pretty close?
Yeah.
It's a little closer. And we did the exact same number of calculations. So a lot of folks say, I like this one better. Like I said, if it's very slow moving, trapezoid rule is perfect. But if it's moving a little bit faster, then this one works. Now, this one is not named after the shape, not directly, okay? Hopefully I can get this back. So this one is named after somebody.
Simpson.
Come on, please. There we go. All right, this one is named after a very famous French mathematician. Sorry, named Omer Simpson. So this one, we hate theorems that are named after people because it's like, what does that even look like, you know? So this was named after the very famous mathematician Omer Simpson, who some of you may recognize. Oh, okay. The famous, like I said, because the famous mathematician Omer Simpson, his head was shaped like a parabola. Makes perfect sense. So he modeled this, at least that's what I believe happened. He modeled this formula after the shape of his head and he was able to do estimations of integrals. Again, this is called, no joke, it's called Simpson's rule. Omer Simpson. You guys recognize that guy? You've studied him in your high school history classes?
Mm.
To some degree? Okay.
What was me, Homer Simpson?
So, given any situation where you don't want to do the integration, maybe because you can't do the integration, if the integral is just out of control. I mentioned this one does have an antiderivative and you're going to learn how to do that one in Calc 2. But if I change this exponent and made it a third or fifth power, then it actually is nothing you could do. So this is called a numerical calculation. I'm not trying to integrate it and evaluate. I'm trying to just number crunch, okay? Newton's method, right? That's an iterative process of number crunching to get us to an answer. We didn't do calculus necessarily in that problem other than taking one derivative. So this is not a calculus problem, but this is a problem we can use to estimate a calculus problem that we could not otherwise do. And it's unbelievably powerful. And you just saw with these two examples with n equals 6, how absurdly close we were to the actual answer. And I need to show you that because now you realize just how powerful this is. Are you going to use this often? No. No. But you would use it in a scenario where you had no other way of answering the question. Because it actually is pretty simple. Okay? Any question on this? All right, so we have begun the application, although this application wasn't technically a calculus application because we didn't do any integration or even a derivative. From this point forward, everything we do the rest of the way is going to be applications. We're going to be doing areas, We're gonna be doing volumes of different types. We're gonna be doing arc length, we're gonna be doing surface area. Things that we can use the integral to answer, and we're gonna get good at it whether we want to or not. The last new material that's going to be on the last exam will be next week. So, in a sense, you guys have a bit of a break. We finish the material for exam 3 next week, and then we have a week off. So which means you now have, I believe you have something like 19 days from the end of the material until the exam. That's a lot of time to prepare, or I guess a lot of time to forget, depending how you look at it. But we lucked out from that standpoint. If next year, by the way, Thanksgiving week will be after the 14th week of class. This year it's after the 13th week. It depends when Thanksgiving falls. 3 out of every 7 years, Thanksgiving falls after the 14th week. Well, those years are really awkward because the day you come back to class, the entire semester is over 10 days later. And a lot of folks say, why are we having a break with a week and a half to go? It does seem odd, but what's worse is a lot of classes, and I don't even want to know, some of you, the day you come back from the week off, have exams. I know people are giving exams Monday morning at 8 o'clock the day you come back. I try to avoid that one like the plague. You guys, your exam is not the week you come back. It's the week after the week you come back because of the natural delay we put in. So that's why we have a ridiculous amount of time to prepare. The practice test has been up for a while. I don't expect anybody's going to look at it until after next week, and I don't think you need to. But at some point, obviously, you want to take a peek at it to make sure you're totally on top of things. Let's go ahead and stop there.
Actually, you press the button, Chase. I'll give you.